Thanks for coming here today. It's a great pleasure to have Tribhi Kathuria defending her PhD thesis. There's an interesting story how Tribhi started doing PhD with me. She took a course with me. She's still pretty interested in whatever I was talking about in class. And then she came to do research with me, and then later said, I don't want to do research, I'm going to go find a job. She went for an internship in Honda in Michigan, and then came back after the summer and told me that I want to do a PhD. Learned a lesson. And then I told her that, well, let's do, some 590 or something and work on some learning problems. And then she told me, I hate machine learning. That's not a good start. How can we work like this? So I said, fine, let's maybe do some value iteration upon VP. And then over the years, I convinced her to do reinforcement learning. So today she's going to talk about learning. And Tribhi also did a lot of work for lab outreach. Jesse created this initiative with Museum of Art and told them, these are the guys, and they never questioned us after that. So we have a very strong relationship with the museum. We take a robot there once a year or twice a year, and the robot every time does something interesting. These days, the robot can have conversation. We have these chatbots. And took a lot of time from Tribhi in my lab, but that's what it takes to do robotics. And you don't see the effort here in the slides, but it took many, many hours to do it, and still ongoing. And proactively, museum reaches out to us, and the Office of Provost encouraged us to get some funding from the university and scale it up. And that's really great. So without further ado, we hear about Tribhi's research, who made me more interested in humans and how to interact with people. Take it away.
Thank you for the kind introduction.
I remember everything.
That's a problem. You remember too much.
So with the chronology, I think now you can kind of tell my thesis is on motion and behavior planning for socially assistive robots. Socially assistive robots are robots we're seeing everywhere around us these days. So in the healthcare industry, we've seen a benefit of using these robots in increasing engagement, which we can use as therapy for kids with autism or as companion robots for the elderly. You can also see these robots in the service industry, where you might find one serving you food, or you might find one showing you around in an office building if you're lost. In the home robotics setting, we still don't know what to do with them, but you can use them for surveillance. You can have them fetch you things around the house. And in general, it's a very interesting space with different applications and different benefits for different industries that we're looking into. One thing in common with all these applications, though, is that the robot is existing in a very human-centered environment. These environments are not modified for the robot to easily operate in. So we must kind of learn how to walk around and interact with people in these hard environments. Like Mani hinted to, our work in this space was kind of inspired with the collaboration with the University of Michigan Museum of Art, and a lot of the research questions were inspired by what we were trying to deliver. So I'm going to break down this dissertation in 3 chapters. The first one, we're looking into more higher level reasoning and task planning for socially assistive robots and scheduling. The third chapter, we look more deeply into human-aware navigation. So we're getting a little more on the lower level planning. And then finally, I look into how we can integrate this progress in foundation models and where the benefit is for socially assistive robots. So getting into the second chapter, where we're looking into task planning and scheduling for socially assistive robots. This work is again inspired by work at the museum, where we want to give a tour of the museum. The people at the museum kind of know where everything is. They know what a tour looks like. They know what the specifications are. And what we're interested in is giving an environment which is also engaging to the people that are visiting this establishment. And we found that with the traditional robotic stack, what we do usually is we build a map representation of the environment. We use this map representation to inform a task planner, which informs a global planner, and finally a local planner that can execute these the velocity commands given out. And then the question that we are trying to answer is how we can effectively encode these human preferences and information that are pertinent to a socially assistive setting. To that end, we propose a three-party framework where we recognize there's three interacting parties in any socially assistive setting. These are providers, clients, and robots. So providers are people at the museum. These are people that tell us where everything is. These are people that employ the robot to perform a certain task. The providers need to kind of understand how the robot is thinking and what it knows about the environment so they can help impart their wisdom into telling it what it needs to do and where what the knowledge base is. And then there's another side, which is the clients, and these are the people that the robot is helping serve. And these people can have different requests, constraints, and questions for the robot to account for, and the robot must share an explainable plan of action that they can modify if needed. So we propose a three-layer mapping architecture for this work. So the one in the middle, if I can get my cursor, is a dense voxel cloud. We use the RGBD images in our environment and a visual odometry to get do some postgraph optimization to get this voxel cloud, which gives us this dense representation of our environment. We also note that this representation is maybe a little too dense for a ground robot with differential drive with circular base. We don't need all that information. What we do need is if you cut everything at the robot height, that's the obstacle space for you. So we use a projected map that can be given to a local planner to avoid any floating base obstacles. That's the bottom layer over here. And then finally, we use a laser scan map to kind of get a floor plan-like method of the environment. And we need that because we're interested in building a topological map of the environment. So the map on the right is proposed by one of Professor Kuiper's students, where we're able to have the different semantic annotations, which are places in the red, pathways in the green, and then decision points in the blue. We take these different map layers and so that the provider can share their expertise given the different sources of information. So this provider can annotate where the robot should go. These we call our points of interest that are annotated in the map on the right. These points of interest, the provider might be interested in seeing from the RGBD data where different artworks are and help it annotate where the robot should go. So we have this augmented map that can inform a planning pipeline, and qualitatively it looks like the result on the right, where the robot is kind of the axis that you see, and the waterline path is coming from our topological map, and it gives you the path down the corridor in green. And the local planner is a dynamic window collision avoidance, DWA star, commonly used in literature, which can follow this trajectory plan that's coming from the global planning. So far, we've kind of come up with an augmented map that can help us plan and go from point A to point B in our environment. What we're now interested is in looking at the tour planner and see if we can further inform or use the human preferences and incorporate that in our higher level planning. To that end, we propose an interactive tour planner. We propose a mixed integer linear program that can take different provider and client constraints, and we model these constraints given kind of our museum problem. So if you're trying to model the provider constraints, they might want you to go to point A before point B, because that might make some sense in the way that you're learning information. And then you also have time constraints where you might want to finish a tour within, let's say, 10 minutes of the time. We also can model and handle client constraints where a client might want to see a certain number of artwork. And you also, if you go to the Louvre, you want to see the Mona Lisa for sure. So we model that as like a weight on the client demands, or we call it. And then finally, we define the cost function. The cost function now has two competing objectives that we might account for. So you want to finish the tour within the time limit that we have and not violate any sequence constraints. And at the same time, you want to drop as few of the client nodes as possible. We compare our planner to two, yes.
How do the providers feel about minimizing the time of the tour? Because I can imagine a provider who might feel that they wanted to maximize the time of the
Yeah. Oh, so I think I should have maybe clarified. So it is minimizing. It's a constraint on maximum time, but it minimizes in the sense that it's going to complete the tour with as many demands, covering as many demands on the tour as possible, but staying within the time limit. So it doesn't go over, but it's not going to minimize. It minimizes in the sense that you don't want to take a long path.
It's a bound, but it's not a minimizing objective.
Yes, it's a constraint. Yeah, sorry. All right, so actually that helps explain this plot quite a bit. So we're always within the constraints, which are the sequence constraints and the time constraints, and we're given a set of client demands. And we compare our planner with a greedy in time and a greedy in demand planner. So the greedy in time planner prioritizes client requests by the amount of time it would take to go to all of these places. And the greedy in demand planner prioritizes the client demands by the amount of demand you have on the current location. And as you can see from the figure, our planner ends up dropping the least amount of client nodes without violating any of our hard constraints as compared to the greedy planners. We also compare the planning times for our methodology planning on different map representations. So we compare it with planning with A star on an occupancy map versus planning on a topological map like ours. As you can imagine, planning on a graph is a lot faster than planning on a grid. And as a result, our planning time for the tour planner improves by more than 80%. So qualitatively, this is what it looks like in our simulation environment, where the start of the tour, you're given certain points you might want to visit and the client might have requested. And then within the tour constraints, we show a smaller tour here. You choose 3 points that you're going to see, and the path is given in pink. And then finally, you need the global planner, which is the topological mapping planner, in green kind of to navigate, and then the local planner gives the velocity commands to our controller. We also extended this approach to a multi-robot, multi-human problem. As you can imagine, when you're at a really big museum, you're going to have a group or lots of groups of people that are visiting at some time. And you're also going to have a fleet of robots, hopefully, to give this tour. So now the problem has another layer of complication where you are trying to match the groups of humans to fleets of robots. And then finally, we execute the tour. So qualitatively, I will emphasize on the extreme case of 50 robots and 250 humans, we're able to solve this within 30 seconds. So in conclusion, for the task planning chapter, we provide a novel provider-client robot framework that can integrate human preferences on the high-level planning and the mapping for a socially assistive robot. And we also see that this tour planning is fast, explainable, and interactive, which is kind of what we wanted for the system. So going into more lower level control, expanding from our previous problem, we looked into using very simplistic planners that always assume that humans are obstacles. and we don't model any dynamic motion. So this part of the thesis looks into how we should be walking around humans in these different settings. Social navigation is a very rich set of problems to work on. There's tons of different scenarios that you could be encountered with, and it's almost impossible, but we've tried in different survey papers to try to understand what the scope of the problem is. For this thesis, we're going to be looking into two of these scenario cases, which is the crowd navigation and the narrow doorway task. So crowd navigation, you have a robot, which the robots here are in blue and the humans are in red. You have a robot in a room and the humans are walking everywhere and you're trying to navigate from point A to point B. And then the narrow crossing scenario, the robot and the human have a narrow doorway in the middle and you're trying to yield kind of to the human or get to the goal if you can. Crowd navigation has been looked into kind of very heavily in the literature. On the left, you'll see the wheelchair robot from Professor Kuiper's lab navigating the hallway. I think this is the Dow building or the BBB building. Yeah, Dow. And the robot is able to navigate around people. It can stop if it predicts that people are coming onto the corridor a certain way. And can safely go from point A to point B. Another popular approach for crowd navigation control that you'll see in the literature is optimal reciprocal collision avoidance, where the assumption is all the people in the scene are trying to avoid each other, and we build sets of possible velocities, and then try to minimize the collision sets. And finally, both the robots will execute plans that are out of collision to get out of crowd navigation safely. Lately, we've looked into crowd navigation in a learning-based setup. One of the more popular simulation setup for this is the one shown on the left, where the robot is navigating a 10 cross 10 grid with humans walking around trying to get to their goal at the same time. And we've seen a lot of reinforcement learning-based approaches trying to solve this task of walking to its goal without hitting people. As you can imagine, there's different reward biases that you can add to your system to account for different preferences. And one of the simplest rewards for this problem you can think is you get +1 if you get to the goal, you get -1 if you hit a human. And you can try to see what kind of policies you can learn. For this thesis, I'm going to argue that we should be learning policies from inverse reinforcement learning, which is the inverse of the reinforcement learning problem. So let's say you're trying to teach a baby how to walk. And in reinforcement learning, you have an environment and you give a set of task description kind of with the rewards. So you tell the baby, walk or go to the goal. And then it's on the baby to try to figure out how to go from point A to point B. The inverse of this problem is if you buy the baby a walker or you show the baby how to walk and kind of figure out how to actually find the joint angles to walk different positions. So inverse reinforcement learning problem is set up as a Markov decision process. So a Markov decision process, if you're not familiar, is a process where your future state only depends on your current state interaction. So I set up the IRL problem as an MDP, where there's a set of action spaces, set of states. You have a set of demonstrations, which are the trajectories you've seen trying to explain the reward. And then finally, a reward function that we're trying to learn here. The reward is expressed as a function of your features of your state. So this P here is a feature of your state and action. And then finally, for each set of demonstration, as you can imagine, when you're, let's say, coming back to the walking problem, there's 50 different ways to walk and everyone has a different specific walk. So there isn't a clear, there's an ambiguity in the learned rewards for every problem. And in literature, we've looked into how to resolve this ambiguity to best match the demonstration data. one of the popular approaches is using maximum entropy solution, where we're working under the assumption that states or actions in our demonstration are exponentially more likely to be seen if they have a higher reward. So maximum entropy deep inverse reinforcement learning, as you can tell from the deep word, can generalize this further, where now your reward can be a nonlinear function of your features, and we're trying to learn the weights theta. So we define the loss function working the maximum entropy assumption, and with some math that I won't go into, your loss is divided into your demonstration loss, which is the LD over here, and the L theta becomes the regularization loss on your weights. And then finally, we take the demonstration loss and we express it on our based on our reward instead, and is propagated as a gradient for maximum entropy inverse reinforcement learning. Intuitively, what I want you to maybe see here is to give an idea of what's going on is the state visitation frequency term. So mu d gives you the frequency of any state being visited in your demonstration set. And the expected mu is the frequency of that state being visited given your current reward prediction. And describing this as gradient, when this goes to 0, you've perfectly matched your demonstration. Trajectory ranking MED IRL loss proposes a trajectory ranking loss on our current formulation. So this is to account for suboptimal demonstration data. So let's say I'm driving the robot in the crowd navigation scenario, and sometimes I get a little too close to the human than I'm meant to be, but it's still useful demonstration data. And what I can do is maybe learn less from that demonstration versus others. So we define a cross-entropy loss where if one demonstration was ranked less than the other one, then you have a less loss, and you end up learning more from highly ranked demonstrations. So coming back to our problem setup, we have a robot. We defined a state space for the IRL as an MDP, which is a 3x3 grid in front of the robot. The actions are to go forward, left, right, top left, and top right. And you have a set of demonstrations where we are driving the robot and it sees where to go. The features used for this work are hopefully intuitive to the crowd navigation scenario. So the first feature that I think is pertinent for learning a good reward for crowd navigation is predicted trajectory, where we have a human walking in the scene and we forward predict where the human will be in the next couple of timestamps using a social LSTM, and that gives us a reward. That gives us a feature information for the predicted trajectory. We also want to model the social distance of the human, so the reward learns to respect the social distance. And you also want the robot to know where the goal is at all times, so we model the distance to goal feature. And finally, to avoid any unseen obstacles, you want to model distance to obstacles. So getting the ranking for this crowd navigation setup, we use a sudden velocity change rate, where intuitively what we're trying to do is trying to, in the least possible way, disrupt the human from walking. So this metric will have a higher, you'll have a higher velocity change rate, means you have a lower rank. So if you saw that the humans were staggering near you, that means that was not a great demonstration, and we're not going to learn too much from that one. So this is kind of what our training methodology looks like. We drive the robot, we collect a bunch of demonstrations, we extract the feature maps, which are going to help us learn this reward. And the gradients are what we talked about, which with the SVF difference being the MEDRL gradient and the ranking loss being the coming from the trajectory ranking. So qualitatively, this is kind of what our approach looks like. I think some of the easiest conclusion to make here is when the humans are walking this way because our agent understands where they're going to be in the future. We rightfully try to go behind them instead of trying to go in front of them. And we're also minimizing for the jerky motion in our trajectory. So to set up the stage, now we're now looking into the narrow doorway scenario. So working with, you still need crowd control, but now we have an extra element of understanding the scene geometry. So what does that look like? So if you're using a crowd navigation controller, like we discussed Orca in the beginning, what ends up happening is you don't account for scene geometry, and even if there is a path you might be trying to go to avoid collision, that path is now blocked, which means you end up in deadlock. There's other parts of literature that are looking into how to resolve this deadlock using multi-agent pathfinding, where you're able to kind of prioritize what agents should go based on where you are. And these are different model-based approaches that kind of explicitly model what should happen in this situation. What we're interested in doing is learning from demonstrations on to how the robot should yield to oncoming traffic without explicitly modeling yielding or any social behavior. So as you can imagine, when you're trying to navigate a scenario, and if I give you this top-down view, I would say, because I'm the demonstrator here, you can see, what I decide to do is I go from here to kind of here near the door to kind of wait out the human so there's enough room that the human can maybe decide to go somewhere. And then wait over here for a little bit. I don't know where the human's going to go. And then finally, when the human is passed and my path is clear, I decide I'm going to go to my goal. And this is kind of the behavior we want to teach the robot to learn for itself. So the challenges of this approach, we're now, compared to the crowd navigation work, we're now working with dense scene data. We're working with top-down images. And then we want to use this data, but we don't want to add any demonstration overhead. So for this work, the demonstrations were collected within 5 minutes. And we are also not, we also want to predict the human motion implicitly now that we have this top-down understanding of the environment. So the MTP setup for this, this new task is this 60 × 60 grid on our top-down view of the environment. And the action space can now be go straight, left, right, down, or stay where you are. And again, we're trying to reason about the reward function. The features, now we're getting away from handcrafted features and we're trying to use raw image data. We also need to give it some understanding of where it is in the episode. And as a result, we need to encode kind of where the human has been from the start of the episode, where you have been at the start of the episode, where your goal is, and then finally to be able to kind of implicitly learn where the human is going to go. We also give it the human's velocity and heading at any time. So when you're working with this dense grid, top-down grid, with few-shot demonstrations, there's a lot of unseen states in our data, which means the robot doesn't do a very good job of generalizing across different states. One way to get away from it is kind of smartly extrapolate these demonstrations. So for each demonstration data, I sample a new start position, making sure at any point I'm not close to the human, and then I go to the next stopping position. And usually the stopping positions are not too far, so the demonstration extrapolation is time-based, so it doesn't completely go in very different directions, but is very close to my demonstration data, but kind of just helps smoothen the reward a little. And then we still note that there's some aberrations in the learned reward, where there might be some states are kind of sampled a little more than others, and then there's certain local minimas and maximas that you'll see over here, but the robot can't really stand on that one pixel over there. So the robot should learn to kind of smoothen out this reward, we use a bilateral filtering loss function where for every pixel, essentially, we're penalizing if your reward is drastically different from the other reward while preserving the edges. And then finally, with the reward smoothing, qualitatively, the reward looks a lot nicer and doesn't get stuck in a lot of local minimas. So this is kind of what the full pipeline looks like. We have a set of demonstrations, and then we extrapolate some parts of that demonstration, which creates like an experience buffer, which we feed that into a reward, like a unit architecture to learn to predict kind of the reward at any time. We also have the demonstration data, and you compare that to the demonstration you get at any point to get the SPF difference, which is the MEDIRL gradient. And then finally, the bilateral filter, which gives out the smoothing loss. So comparing our approach to other baselines, which are more rule-based, on the left, we see the ORCA agent, like we discussed before. It has collision sets for avoiding dynamic obstacles. And when these collision sets are all in a scene with static obstacles, then you end up in deadlocks. The ORCA backoff agent is a rule-based agent where when it detects deadlock, it decides to back off to its start position, for the lack of a better idea of where it should back off to. So it will wait, decides to back off, go to the start position, and then wait for the human to pass by before it goes to the goal. And then finally, the IRL approach is able to correctly assume I'm going to wait for the oncoming traffic and be out of the way, and then finally waits for the robot, but sometimes gets stuck in some local minimize over here, as you see, but it will, I think in this case, it eventually gets out of it. It does. And then our approach, again, waits in the middle for the human to pass. And finally, you'll see that once the human is cleared, we start to go to our goal. Quantitatively, we ran our experiment with 13 different start and goal positions, and we collect the success rate of different agents. The ORCA agent has 100% success rate when there isn't any deadlock. So the episodes 3, 7, and 9, you'll see it does very well. For the ORCA backoff agent, it does mostly well for a lot of the episodes, but it does end up failing when your start position isn't the most optimal position to wait for the human. So for episodes, I think 4 and 12, we don't do so great. The IRL agents are able to kind of yield to oncoming traffic, and the MEDIRL agent sometimes gets stuck in local minimize and has a success rate of about 84%, while our smooth MEDIRL has a success rate of about 92%. We also are interested in not disrupting human motion and also getting to our goal as fast as possible. You will note here that the ORCA backup agent had a decent success rate, but does take longer because it does have to go back to its start position, wait for the human. So on average, it adds about 20 seconds to the human trajectory time and about 30 seconds to the robot trajectory time. So in conclusion, this work looked into more lower level control in how the robots should navigate around humans. We presented inverse reinforcement learning based solution for 2 different social navigation tasks, and our methods exhibited higher success rates and were less disruptive and kind of faster. Finally, we're interested in kind of evaluating how these foundation models that are coming out now can be used into or where they can actually fit in the socially assistive robotics pipeline. So large language models and vision and language models are being used to kind of act as reasoning agents for a lot of planning tasks these days. The one on the left is a tidy bot where it can take a language prompt such as sort the laundry into lights and darks, and it's able to in loop question the vision model to get the objects and then ask the large language model to reason about how to tidy that object. More closer to our work is the work in social navigation on the right, where they use egocentric images and do some prompt engineering to get the direction of moving and the speed of the robot at any time instance to give kind of like it creates like a cost map and then has other obstacles and other features included in it as a cost map and then chooses informatively which trajectory to choose. So we were interested in seeing if we could use these large language models as reasoning agents for our task as well. So for the door navigation task, we kind of want the agent to tell us how good or bad our demonstration data is. So the way that we set up the prompts is the first one is the developer prompt, where you tell the GPT agent kind of the task description, which in this case is the yellow is the robot's past, the teal is the human's past, and the magenta star is where the robot is trying to go. And I asked the agent to evaluate how good the robot's chosen action is, which is in red. And if you don't see the red, that means the robot has decided to stop. The agent in itself, if just given that task with one shot, inference is not very great at it, but it does get better if I kind of give it examples of how to do it. So to kind of explain to the GPT agent how to label this data, I tell it, evaluate the image attached, and then I tell it kind of act as the agent and the assistant prompt, and I tell it, well, I would rank this 3 on 5 because the robot should be going to its goal as the human has passed. And then I give it another set of examples where the robot actually decides to go to the goal after the human has passed, and I rank it higher. And then finally, once it has a set of example prompts, it can learn to actually answer the user prompts where I just give it evaluate the image ahead, and the assistant is able to give me a ranking and a reasoning for why the ranking was assigned. So going back to our door navigation using IRL, we had a trajectory ranking methodology to encode preferences into our IRL learning pipeline. We were working with binary cross-entropy loss. For this work, we kind of generalize it to a multi-class entropy loss, where, as you can imagine, now we have a rank between 0 to 5, and we have different weights assigned to different classes. And this loss function can kind of help us learn more from highly ranked demonstrations versus lowly ranked demonstrations. So does it work? Not quite. And I think the reason is the task that we've chosen for this GPT agent to evaluate. The success rate for the agent, IRL agent, drops down to about 76%, down from 92% for the SME-DRL agent. And on evaluation, I looked at the data where, compared to a human who's ranking the system, in this case, my mom, is you compare it with the ChatGPT rankings, and we see that the GPT agent is a little more conservative and ends up labeling some of the data with lower ranks. But the problem is inherently in our setup, where most of the demonstration I'm sharing is pretty good, and there's less information to be gained. The exploratory question here that I'm interested in answering is, can it help us learn online though? Like, it's reasonably okay at labeling this data. When my agent fails that I trained it offline for deployment, can it help me label this new data that I'm getting and help me supervise and train and do better in this unseen setup? So we kind of looked into social navigation and see how the GPT agent will kind of fit there. Didn't do great for the task that we've chosen, but what it does do very well is talk to people. So I think what Mami talked in the beginning of my introduction as well, we've done a lot of demos at the museum, and every year we try to bring a different version of our robot. So this is the robot greeting, acting as a greeter at the museum. There wasn't a lot of room. It was like an experimental setup where there wasn't a lot of room for the robot to walk. So we were just at the door talking to the people. And the GPT agent is then given the prompts kind of very similar to what I showed in my methodology to ground what the different artworks are and is able to talk to people in an informed manner.
Meaning of art, I like that one.
Oh, you should ask it.
Hey, fetch. What's the meaning of art?
Art is a way to express yourself. It can be anything from a painting to a sculpture to a song.
You can see me scared every time it answers. And then finally, the next year, we actually took a fully fledged tour guide into the museum. In this case, we used a perception module to build a map of the environment. We were using a particle filter to localize, and we use a star to kind of navigate the room. We did have crowd control, where I asked everyone to not please jump in front of the robot. And we also kind of included the interaction module where you could ask it different questions and even a kind of contextual questions, because every point in our map with the provider was localized to where the robot should stand and also what the artwork is. So you could go to an artwork and ask the GPT agent, what is this? And it would understand based on where it is in the map, what it should say and what painting you're referring to. And we were able to successfully complete the tours, more like a demo. And we did it for mostly kids at the museum who had a lot of fun talking to it. So in conclusion, this thesis has looked into providing looking into task planning and scheduling, a high-level methodology of incorporating human feedback for emotion and behavior planning for socially assisted robots. We also present a way or evaluate ways for using inverse reinforcement learning to kind of navigate complicated environments with humans in it. And then finally, the last chapter looked into how we can better incorporate foundation models for understanding social behavior as well as for interacting with people in the socially assistive setting. These are the most relevant publications. All of our software is open source. And then finally, I would like to thank everybody for coming, and especially thank you to my committee. Mani has been a source of constant support, has shown a lot of faith in me. He gave me a PhD project when I was a master's student and told me, you've got this and you can figure it out, and that's become my PhD. I would like to thank Jessie for her support in my PhD journey. She has always emphasized trust and human side of things that maybe me and Mani would not have thought too much about if Jessie wasn't there. And finally, I would like to thank the other Jessie. You've been a constant pillar of support and somebody to really look up to, going from day one in the Rob 101 class, learning from the best to teaching Rob 101 with the best. You've definitely been an example of what a professor of your stature looks like. And then finally, to Professor Kuipers, I would like to thank you for your immense support through the whole process. We've talked about this project through all parts of the journey throughout my PhD with you, and your feedback and your kind of understanding of this problem has really informed my research direction. So thank you. And finally, Joyce, for kind of bringing the CS touch to my my dissertation. And as soon as I remember in my proposal, I said, I want to see, I want to work on this large language model. And she's like, I want to see a failure case. And there you go, Joyce. Finally, I would like to thank my lab and my collaborators. You guys have been an amazing source of support. Justin and Cynthia, especially, we started our PhD together and they've been with me every step of the way. And I cannot thank enough how much you guys have helped me through the whole process. And I would like to thank the amazing robotics staff. Anyone that you email at odd hours. Denise was on call with me this morning where she's like, did you get the form? And so I would like to thank them all for being the best support team I could have asked for. And finally, an acknowledgement to all of my friends that are here. If you don't see yourself on the slides, I'm sorry, I tried. You guys have been, and you guys have made Michigan feel like home, and that's quite a wonderful thing. Especially, I would like to thank the Zora family that has opened their house to me every Thanksgiving, every Christmas that I couldn't go home. You guys have been like a second family in Michigan. We love you. Feel like home. Thank you. Finally, I would like to acknowledge my family, my parents who are here and have been a constant source of support, my grandparents who I love dearly, who are very proud of where I am, and finally, the friends. I would like to thank my extended family and my friends for their complete impatience through the whole process, for asking me every day, when am I done, and how much do I still need to work? Finally done. I think you guys can stop.
It's never done.
And with that, I would like to say thank you. And I would take any questions.